Let's do the consensus for the buggy car lab. Here's what you did. Okay, you took your car and you let it go, and you recorded time and position in your data table. So time in seconds, position in meters. Now some of you had graphs that looked like this, where your car was going kind of slow. You started, you moved away from the origin. Some of you had graphs that looked like this. Slow cars moving back towards the origin. Some of you had cars that looked like this. Steeper slope, because they were moving fast. That was the red cars. Okay, and then, or maybe you had a car that moved something like that. Fast cars moving towards the origin. But all of them had the same basic mathematical structure when you develop from this the mathematical model. And so our linear equation, y equals mx plus b, these are all straight lines, so we can use y equals mx plus b to describe them. But this is our crutch equation. And so what we're going to do is we're going to say, no, y, really this was the position axis. So I'm going to call this, position equals, now what was this? Well, this is the slope of it. Now, if the slope, if you had a blue car, it was roughly 0.4 or 0.5 meters per second. If you had a red car, it was 0.4, 0.5 meters per second. If you had a blue car, it was about 0.2. Some 0.3, 0.2, 0.1, somewhere in there, because you were only operating on one battery. But in any case, if you were moving towards the origin, you had a negative slope. And if you were moving away from the origin, you had a positive slope. Okay? But in any case, you had a slope. And the way you got the slope is you went delta x over delta t. You see, I'm not going to use p for position anymore. This is the last time I'll ever write p for position. Instead, from now on, we're going to use x for position. X equals, now what's the slope? Delta x over delta t. What's our horizontal quantity? Time. Plus, and then what is this? Well, for all of these, it was my position, the position of my buggy car when what was true? When time was equal to 0, right? My starting position, the position when time was 0. So we're going to call this x naught. And this right here, oh, we're almost there. Now, this slope, the slope of a position versus time graph, is very important. And we have a name for it. Okay? Delta x over delta t, by definition. Okay, if you see this little 3-barred equal sign, that means by definition, delta x over delta t is called average velocity. So, and the variable we're going to use for average velocity is just a cursive v like that. At least for now. We'll change it a little bit later. So, we have now a mathematical model for all objects that move with a constant velocity. X equals the velocity times time plus my starting position. So the position of my car is going to be equal to where I started my car plus how much I changed my position by moving. This is how fast I'm moving and in what direction. That's my average velocity times time. So this is my mathematical model for constant velocity motion. So this is the mathematical model for constant velocity motion. Now, what do I mean by constant velocity? What was true about the cars? Did they change speeds? No. Did they change directions? Well, some of them curve a little bit, but let's pretend they just move in a straight line. So if you're moving in a straight line, you're not changing direction, you're just going, and you're not changing how fast you're going, that's called constant velocity motion. And this is what we're going to study this semester. I mean, this unit, Unit 1. And this is the general mathematical model that we're going to use to understand to understand constant velocity motion. This mathematical model is very powerful. It's going to give us the ability to predict what's going to happen before it happens. Okay? It's got predictive power. It also describes very precisely what the cars are doing in a very succinct little way. For example, I look at group 1. Your mathematical model was x equals 0.6 meters per second times time plus 9.5 meters. Negative. Yeah, that's right. I was just thinking, whoa, it started 9.5 meters. Okay? This described exactly what their buggy car was doing. Okay? Can I figure out where's their buggy car going to be at 10 seconds? Can I figure out where their buggy car is going to be at 10 seconds? Absolutely, by using this mathematical model. Okay, that's the power of physics right there. Okay, now, so that's it for the consensus.